Okay, so in section 3.4 on harmonic functions, we're going to start with just the definition, and then we're going to go in and then start our examples. So a function of two variables is called harmonic if it solves Laplace's equation. So namely, when you take the second derivative of phi with respect to x and the second derivative of phi with respect to y, and you add them together, you get 0. So this equation here, this is called Laplace's equation. So if phi solves it, we say it is a harmonic function. Fantastic. So how they enter the picture that we have is that well, harmonic functions are special. So it's just the Laplace's equations are special, and it turns out that if f is analytic, in a domain, then the real and imaginary parts of f are harmonic. And why is that? Well, let's just check real quick. So both of the checks are similar, so I'm just going to do the real part. So f is u plus iv, and we're going to check u. Now let me remind us that being analytic tells us we have access to the Cauchy-Riemann equations, and the Cauchy-Riemann equations tells us ux is negative vy and uy is negative vx. All right, so the claim is that u is harmonic. So we want to show that u is harmonic. So the partial derivative of u with respect to x twice plus the partial derivative of v with respect to u with respect to y twice should be 0. So let's check that. All right. So let's look at partial squared u, partial x squared plus partial squared u, partial y squared. And we're going to make use of Clairaut's theorem, which tells us that if our functions are nice enough, these functions are nice enough, then the mixed partial derivatives commute. So that's what Clairaut's theorem is going to tell us. Let's start by rewriting this. So this is take the partial derivative with respect to x of ux plus the partial derivative with respect to y of vy. That's what that means, to differentiate twice. Uy, sorry. Uy. Ux is, by the Cauchy-Riemann equations, though, vy, and uy is, by the Cauchy-Riemann equations, negative vx. So both of these, we can rewrite the first one is partial squared v, differentiate with respect to y, then x. And then the negative will come in front, and this is partial squared v, differentiate with respect to x, and then y, or however order you learned it. But the mixed partial derivatives commute, that is, these quantities are equal, so they subtract to 0. And the imaginary part is the same. So what this tells us is that our real and imaginary parts of our analytic functions are in fact harmonic, and harmonic functions again are special. Oops, sorry, that was my dog. Let me also just name one more thing here before we do lots of examples. There's an operator called the Laplacian, What does it mean that it's an operator? It means that it breaks up under addition and scalar multiples come out. And this operator is often denoted with, well, it's denoted in a couple of ways. Uh, One of the ways is with an upside down triangle squared. And oddly enough, the other way is with the triangle the other way around. But anyways, we're going to use what the book's notation is. So this is nobla, this is called the nobla symbol. So we say nobla squared. And what it is it's the operator, so it does something to some set that differentiates with respect to x twice and differentiates with respect to y twice and adds them together. Okay, so this quantity here that we sort of think about as doing to what our, let me find a color here, what we do to our real and imaginary part, we do this operation to them. So this is our operator that operates on our real and imaginary part. This is called the Laplacian.